Hello class, welcome back. I hope you're feeling good about exam 1. If you have questions about it, we can cover it briefly on Monday. The scores, your scores will be posted not on iLearn, there's no convenient way to do that, but through Gateway. And once they are posted, I will announce it, send out an email, along with some instructions on how to get your score. If you can't, after all that, you can't get your score, that probably means, it almost surely means that there's something wrong with the way your student ID or your name was bubbled. The machine, as I've said, can be unforgiving, but there will be a record, and we will just email me and we'll track it down. I think you can also email the testing center. And that'll be probably at the end of this coming week or early next week. Sometimes it takes a while. All right, let's talk about cognitivism. Today, we're going to talk about information processing psychology. I think we'll get to Miller and the magical number 7 plus or minus 2, which is 5 through 9. Well, I don't think we'll get to totes. No, we won't. This is Claude Shannon, and he's considered the founder of information theory. Is that fair to say? He played a huge role in what we now regard as information theory. Why? Well, he's an engineer. He's not a psychologist, and he's not trying to do psychology. I believe he was working at Bell Labs when he started thinking of information in this way. And he thought that we could approach information mathematically, that we could quantify it. And at the time, people, and still, when you think of gaining information, it's, I think, natural to say what happens is you get a fact or a bunch of facts, and we could count those. Why can't we just quantify that? So sentences like water is H2O could be pieces of information. He didn't think it was exactly that. He took another approach. And by the way, when we try to do this, it always reminds me of something Galileo said about furthering our scientific knowledge. I don't have it verbatim, but it was something like we should measure what we have mathematized, what is mathematized, so lengths and weights and so on, and we should make mathematical the things that we haven't. And information at the time was one of them. So along those lines, doing what Galileo thought we should be doing, Shannon proposes that we understand information not as the accumulation of facts or sentences or propositions in our head or in our books, but as the elimination of possibilities. And here, possibilities are what philosophers call epistemic possibilities. Epistemic means having to do with knowledge. So think of it this way. When you eliminate a possibility that's epistemic, it's a kind of for all I know belief, or for all I know possibility. So you're coming home and you have a roommate, and for all you know that your roommate's car is in the driveway, and for all you know it isn't. And the moment you see the car in the driveway, you've eliminated that possibility for all you know that it isn't, right? So that's what information is, as Claude Shannon sees it. And we can encode these pieces of information in the form of binary digits. So roommate's car in the driveway, 1 if it is, and 0 if it isn't. Information can be trivial, or you can get trivial answers. So imagine you ask me if it's going to rain next weekend, and my answer is yes. I've eliminated the possibility that it does not rain. But if instead I say, yes, it's going to rain unless something happens to keep it from raining, I've basically said, yeah, it's either going to rain or not, and that eliminates no possibilities. So that has 0 information. If an astronomer tells us that we will see a comet visible to the naked eye on December 3rd, 2023, in a particular location of the sky, not just in the northern hemisphere, that's a lot of information. It rules out all kinds of possibilities. Seeing it earlier, later, seen it in different regions of the sky, and so that's a highly informative prediction or claim. Now I'd like to motivate all this with a quick little thought experiment. Imagine there are 20 doors in front of you, and a prize has been placed behind one of them randomly, and your job is to figure out where the prize is in as few questions as possible. You get to pick. But let's imagine you have to pay for each question. And you're allowed to ask whether it's behind any set of doors. You're not forced to pick just one door at a time. So you can pick any set of doors you want and ask, is it behind that set of doors? So ask yourself now, before I start looking at possible answers, what's the best strategy here? How can you minimize the number of questions you ask? What kinds of sets or what kind of set of doors would you pick? Here's a bad strategy. Here's what you should not do. Is it behind door 1? That's a bad strategy because, remember, it's been randomly placed. It's almost surely not behind door 1, so your answer is probably going to be no. It could be yes, in which case you'd be lucky. You'd get it, the prize in as few questions as possible, 1. But it's probably going to be no. And what happens with no? That rules out very little. It just rules out the possibility that it's behind door 1. So very little information. You now know that it's behind doors 2 through 20. Not a very good strategy. Another bad strategy is to say, is it behind doors 2 through 20? In that case, the answer is almost surely yes. And again, all it does, the yes just rules out the possibility that it's behind door number 1. So what should we do? What we want to do is cut the possibilities in halves, or as close to halves as possible. So for example, is it behind doors 1 through 10? So if you were thinking that, good job. That's a good answer because the answer is going to be yes or no, and it's 50% given that we've randomly placed the prize. And so you're going to get a yes or no, but if you get a yes, you've ruled out the possibility that it's behind 11 through 20. And if you get a no, you've ruled out the possibility that it's behind 1 through 10. You've acquired the same amount of information, a significant amount of information in each case. Now you could have asked, is it behind doors 11 through 20, or is it behind all the odd doors, any of the odd doors, or is it behind any of the even doors? There are different sets you could have picked. As long as you cut the options in half, or roughly in half, in cases where you can't, you're following a good strategy. It's an efficient strategy. Now that, let's say I ask, is it behind doors 1 through 10? So I'm here, and let's imagine the answer is no. So I know it's behind doors 11 through 20. My next question might be, again, cut the remaining options in half. My next question might be, is it behind doors 11 through 15? And at that point, when you're working with fives, if I get let's say I get a yes, you can't cut 5 perfectly in half, at least not 5 doors, and so then you just break it into 3 versus 2. But that's the way you can ask questions most efficiently. So let's review. Each answer is yes or no. Each question is. Each answer eliminates some possibilities, and each answer increases information, but we want to be judicious in how we can maximize the potential increase of information, and the way to do that is to break the options up in half, or as close to half as possible. That allows us to take the yeses and the nos and think of them as ones and zeros. So you just encode yeses as ones and zeros, the nos as zeros, and this is where we get this idea that computation is all just ones and zeros. It's just, imagine a science fiction show or movie where they have ones and zeros streaming down the screen. And we call these are binary digits. A digit is a finger, and binary is 2 options, right? And your finger can be up or down, and that's been contracted. That's where we get the word bits, a measurement of information, a measure of information. It's just a contraction of binary digits. And these bits, these ones and zeros, are not restricted to numbered items. You can, like I said, you can assign bits to the question of whether your roommate has parked in the driveway, a 1 and a 0. Yeah. Okay, I'm sure some of you have heard of or played the game 20 Questions. It's a kid's game. Well, it doesn't have to be a kid's game, I guess. You think of an object, one person thinks of an object, any object. It could be an apple, a windmill, whatever. And the others have to guess the object in 20 questions or less. And of course, they're going to ask only yes or no questions. They can't ask, what's the object? So they say things like, is it living, right? And let's say you picked windmill. You secretly are thinking of a windmill. You'll have to say no. And then they might say, is it an artifact? Is it made by humans? And you'll say yes. So by saying no to is it living, you've ruled out all the living things. By saying yes to is it an artifact, you've ruled out all the non-living non-artifacts like rocks and whatever. I mean, we don't make rocks, of course. And their job is to try to divide the remaining possibilities, epistemic possibilities, in as close to halves as possible, because they know that they want it to be the case that if you say yes, you've eliminated as many possibilities as possible, and if you say no, again, you've eliminated as many possibilities as possible, as many options as possible, let's say. And to elaborate on this, I'm going to direct you to this website. This is 20q.net, and whoops, good, 20q.net, and it plays a version of 20 questions. You are not playing, you're not the question asker. It's not thinking of an object and answering your questions. It's in fact trying to guess the object you're thinking of, and there are no humans behind this playing the game and directing it. It's all automated. It began not doing a very good job, and it now does a pretty good job, as you will see. So I'm going to direct you to this, and I'm going to ask you to, this will be in the email announcement, to play at least one round. And notice that they have the Marvel version, the Star Wars version, etc. And then they have the classic 20Q that allows you to select any of these options, these language options. So we have Think in American, French, and Chinese, and so on. And it's not Think in English, it's Think in American, because over here we have British, and then we have Canadian, right? And that suggests strongly, that shows that Americans play 20 questions differently than Brits and Canadians. We might answer questions differently. And there's a trivial sense in which that should be obvious, because when an American says the word torch, they're imagining wood that has fire at the end, and in British English that means flashlight. Or when we want to look at the engine in our car, we pop the hood, and we call it the hood, but in British English it's a bonnet. And then there's the whole thing about fries and chips. They got it all messed up. It's their fault. Okay, so we're going to think in American, and you can fill this out if you want, or you can just hit play. And we're not going to go through the whole thing, but look what it's encouraging us to think of. There's a harbor. Whoa. Okay, yeah, Onco. I don't know how to pronounce that. An ice pick, right? What did I say? Apple. I said windmill, right? So you're going to answer this. If you did apple, that's probably going to be a vegetable. And after that, you're always going to have these options. It's not just yes or no. So this is not binary, but think about what the system has to do. It has to think of questions that will maximize information, because it's trying to get the answer in 20 questions or less. Now, apple, is it hard? I guess it's yeah, I guess it's hard. Is it used to make salads? Should I say sometimes or yes? I'll do sometimes, right? Is it green? Well, yeah. So is it sometimes or is it depends? Yeah, it depends. Is it a root vegetable? Okay, so you might want to try apple. You might want to try windmill or something. I suggest in the first round, just imagine that you're playing it with a human, and you're not trying to uh, outwit them by coming up with something really strange. So play it one round that way. Just think of a normal object. Maybe you're playing with some kids, and then next time you might want to try to trick it. And I'll say more about that in the email. That is, I'll say more about what you need to do in the email when you play a round or two of 20 questions with this program, 20q.net. Remember, the job is to balance the options, ask questions that if it's a binary situation, cut the information in half. I once played 20 questions with some kids, and they were just at that age where you're starting to figure this concept out. And so one of the kids, we started the game, and one kid raises his hand and he goes, "Oh, is it a frog?" And his friend who was sitting next to him kind of just he just does a face palm because he knew that that's a throwaway question. The probability that I'm thinking of a frog is extremely small. And so I'm probably going to say no. How many options have I eliminated? Well, I've eliminated all the frogs, but there are tons of other things in the universe of things I could be thinking of. Uh, and so a better question would have been, is it an animal or is it living or is it not living? There's the flip side of that. And his friend had seen this, right? So we'll talk a little bit more about that on Monday after you got a chance to play 20q.net. Bringing it all back to Claude Shannon and information theory, psychologists saw that we now have a way of scientifically understanding information and how information is processed. And so instead of doing introspection and thinking about what's going on in our mind, introspecting what's going on in our mind, and running into the kinds of problems they were running into, instead of thinking of what the mind does as essentially conscious, private, and introspectable, as James does, they thought there might be another way we can think of what the mind is doing. And that is, we can look at not just the stimulus and response relations, but we can open up the black box in between them, and in a sense, we can make hypotheses about how information is being processed between the stimulus and the response. We are not asking people to introspect and recording their answers so much as formulating hypotheses about how information is processed. So just as a computer takes input to output by processing information, maybe we should think of the brain or the mind as also being an information processor. And you can see why this is now heading us in the direction of this idea that the brain is a computer. So when I say opening up the black box, remember I've sometimes on the board I've had like stimulus here and then a box and then as output response. And this is exactly how people were thinking about it. So here you have stimuli coming in, affecting some sensors, and then you have this short-term store, right? You have a selective filter. This is Broadbent's model of attention. We just get a shower of sensory information all the time, and we have a selective filter. We're able to attend to some of it and kind of rule out the rest. We have this processor with limited capacity, and then some of it gets stored in long term. We also have an output system. So here's the black box, and then the effectors would be the things that realize motor commands, for example. So you have the input over here on the left and the output over here, or we should say stimulus or stimuli to make it plural, and then the behavioral responses over here. For some reason it's pointing upward. Okay. By the way, in the book, This is reproduced in the book, but they left out that little arrow. So if you're scratching your head over how this thing would work without an arrow here, that makes sense because there should be an arrow there. So this is Broadbent's model, and he proposed that we get all this stimuli from the environment, and he knew that we're allowed to that we could attend to certain things and screen out others. But his hypothesis runs into a problem, and this is good for in science. You want hypotheses that are testable, or that can be proven wrong. You don't necessarily want your hypothesis to be proven wrong. Some people cherish their hypotheses, so they don't want them to be proven wrong. But if it's not testable, a lot of people think, maybe with some rare exceptions, that it's not science. Okay. We also use the term falsifiable. So this is falsifiable in the sense that it makes certain predictions that if they turn out not to hold, would falsify the model. We're not using falsifiable the way that some people use it when they talk about falsifying data or cheating, making up stuff. No, we're just talking about we're just saying that the hypothesis or the model makes non-trivial predictions about what we will observe in the world. And this one does. It turns out that a pretty intuitive and now well-studied observation seems to create a problem for this model, and it's called the cocktail party phenomenon. So imagine you're at a party and you're listening to someone who's talking to you, and there's a lot of background noise because other people are talking, and maybe there's music and there's dishes clanking and so on, and you're able to pay attention to this one person, even if this person's voice is quieter than some of the voices around you. Okay. And particularly the cocktail party phenomenon is when someone nearby uses your name, and they might speak it more quietly than the person you're talking to, but it distracts you. You will pick up easily on your name being spoken when you're not paying attention to it. Now, it turns out that Broadbent's filter model of attention can't account for that. According to Broadbent's filter model, the selective filter does not, if you're focusing on what a person right in front of you is saying, then you're not processing the other words spoken for their semantic content, that is, for their meaning. You're not paying attention to the meaning of the words. Now, loud noises can distract you. Volume can distract you. So if a bunch of dishes clatters to the floor, you might be distracted merely by the volume of that. But if a quieter stream of language is going on behind you or over to the side or something, the volume's not going to distract you, but we know that speaking your name will or can. This, by the way, is Broadbent, and on the right is Ann Treisman, who came up with an alternative, because it's a kind of a commonplace observation that the cocktail phenomenon is real, the cocktail party phenomenon is real, but she ended up studying this, and as I said, Broadbent's filter model predicts something that just doesn't happen, that we would never be distracted by meaningful utterances that are low volume, right, like our name, right? But in fact, we are. And so it's this refutability of the model that actually is a sign that the psychologists were doing science. And in response, Treisman proposes a modification of the model called the attenuation model. And really, the main difference is just to say that instead of completely screening out the words that other people are speaking and paying no attention to their semantics, not evaluating their meaning, not evaluating their semantic content, We just pay more attention to the semantic content of some things and less attention to the semantic content of others. So they didn't throw out the entire model. They took Broadbent's model and they took out the filter and replaced it with an attenuator. To attenuate, by the way, means to make thinner. So you can see over here, making thinner. And by the way, this is just another image. I'm not teaching the model itself as you would learn about it in a psychology class. And so, but I'll say a little bit about it. So for example, one experiment involves, one type of experiment, they ran a whole bunch, involves listening to different voices, one in one ear and another in the other ear. And they'd say, listen to the voice on your left, and try to ignore the voice on your right. And then of course the voice on the right would do certain things. It might say your name, or it might say something else. So each word can be assigned a threshold. We can discover the threshold of the word, threshold for perception, that is. And so your name has a low threshold. It's easy to distract a person by using their name. And so does the word fire. The fire has, so if the voice in the unattended ear says fire, you're likely to be distracted. And then they can test whether you were by asking you, was this spoken about? Did this voice say that? So they can ask you about the other voice that you weren't supposed to be paying attention to. And also they can test whether you were distracted from the voice you were supposed to be paying attention to by asking you relevant questions. Notice that we are now thinking about the brain as an information processor, and we have scientists proposing different models, formulating hypotheses. They are testable, but they are hypotheses not necessarily about private, introspectable ideas being associated in the mind from some first-person subjective point of view. They're creating hypotheses or models that you could, they look like the kinds of models you might propose for an actual computer. So the concept of the black box comes from computer engineering, where you could imagine, let's say we had a computer, we weren't allowed to look at the circuitry, we weren't allowed to open it up and look inside, but we were allowed to provide it with input and look at the output and make, discover things that way. And in fact, you can do that. So in a previous class a while ago, and later we're going to talk about this again, I distinguished between primary and incidental effects. If you have a black box and you know it multiplies, but you don't know exactly how it multiplies, there are ways of eliminating possibilities. So for example, and we'll talk about this later in class, but really quickly, one way of multiplying is just to keep adding, right? So 37 times 17 might be add 37 17 times. And the other way is the way you were trained to do as a child, which is called partial products. And so you start with the ones column, you multiply, you carry, and you go through it in that way. And it turns out that if an algorithm follows the successive addition method, then you can discover that by seeing how long it takes for the computer to produce the output. So 37 times 2 will not take as long as 37 times 99. It will take longer. And then you can figure out by looking at the time profile, you can get a pretty good idea of how information is actually being processed, right? And so you don't need to ask questions about consciousness and introspectable private ideas and so on. You don't even need to entertain those concepts or include them in your ontology to do this. Now, having said that, I got to point out we do have the word perception here. Unintended words have thresholds for perception. You might know that Watson would not like that. He'd say if you're going to use the word perception, or let's say more broadly, a behaviorist would say if you're going to use that concept, it better be cashed out in terms of stimulus-response relations. But anyway, they are formulating these hypotheses about how information is being processed. Already, just talking about information being processed is a step away from the strongest forms of behaviorism. Okay, let's talk about Miller and the magical number 7 plus or minus 2. This, by the way, is his paper, which begins dramatically. My problem is that I have been persecuted by an integer. For 7 years, this number has followed me around, has intruded in my most private data, and has assaulted me from the pages of our most public journals. This number assumes a variety of disguises, being sometimes a little larger and sometimes a little smaller than usual, but never changing so much as to be unrecognizable. The persistence with which this number plagues me is far more than a random accident. There is, to quote a famous senator, a design behind it, some pattern governing its appearances. Either there really is something unusual about the number, or else I am suffering from delusions of persecution. By the way, I'm pretty sure, but I guess I don't know that that senator is a reference to Senator Joseph McCarthy, who around that time was pushing the Red Scare, was concerned about communism infiltrating America, and so Miller is, of course, that was tongue in cheek, in case you didn't get it. Miller is pointing out that, or arguing that there's a significant number behind a lot of our behavior. He goes on to argue that our judgment and our memory are limited, and when we do experiments, he keeps finding the number 7, or sometimes this might be a 6 or an 8 or even as high as a 9 or as low as a 5 plus or minus 2. But in all these experiments, like discriminating tones or pressing buttons where you need to categorize things, we do fine if it's 1, 2, 3, 4, right? Don't really make errors in those cases. But once you get to 7, the error rate goes up significantly, and we don't do very well after that, at least not at first, right? And so it appears that we can only handle about 7 chunks of information at a time. This holds for judgment, this holds for memory, and even and for behavior that's associated with judgment and memory. So that's interesting. There seems to be this barrier, this limit, this capacity limit. Now, then what explains the fact that we can get better and process more chunks later? The brain doesn't grow new lobes. The physiological changes in the brain, which weren't known about in the way that we know about them today, but those changes, he didn't think they could be that drastic enough to bring about changes where we literally get the capacity to handle more chunks of information. We had to have some other way of doing it, and his proposal was recoding. So the question is, you could think of it this way. Imagine learning to play chess. If you know how to play chess, remember what it was like. You had to learn all the ways that all the different pieces could move, and then you had to come up with certain strategies. You had to learn the rules. That's a lot of chunks of information. Of course, the novice chess player has a lot of trouble at first, but the expert is seemingly juggling all those chunks, far more than 7, far more than 9, seemingly juggling all those chunks at once. How does the mind do that? His answer is you don't really juggle all those chunks at once. What you do is you take some chunks and you put them together into one chunk. That's what he calls recoding. We also call it chunking. Here's a quote. A man just beginning to learn radio telegraphic code hears each dit and da as a separate chunk. He's talking about Morse code. Dot, 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 did, or dit, 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 dot, 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 right? So that's SOS and how they sent telegrams in the old days. Soon he is able to recognize these sounds, organize these sounds into letters, and then he can deal with the letters as chunks. Then the letters organize themselves as words, which are still larger chunks, and he begins to hear whole phrases. And of course, this is how we read, right? We go from, as children, sounding out the words, looking at each letter, struggling with the completely irrational spelling exceptions in English. And we get to a point where we can read fluently. Recoding also involves hierarchies. So think of the motor movement that you use to tie your shoe. At this point, it's probably you just think to yourself, I'm going to tie my shoes, and your hands just kind of seem to do the work. And yet there was a time when you had to think your way through it. And so there's the hierarchy idea is that there's a chunk, tie your shoe, and that is composed of smaller chunks that involve making a loop and so on. So if I told you you had to learn a 10-digit number, immediately remember it, I'm going to take it off the screen, that you might feel a little anxious thinking, how am I going to remember 10 digits? But look at this number, 41574719445. If you had to remember it, what strategy would you take? And living in San Francisco or in this area, you might have you can look at the 415 as one thing. You can chunk it. What else could be chunked? Well, if you thought, well, 747, that's an airplane. 1945, that was the end of World War II, right? These numbers happen to be significant, and I tailored it that way because some strings of numbers aren't as easy to imagine as being meaningful, but this one is. And so this becomes 3 chunks, not 10. So you just have to remember San Francisco area code, airplane, end of World War II. And if you would know what those things are, 747 is just one concept, 1945 becomes just one concept, then you've successfully chunked 10 things into 3. And he thinks this is our strategy. That's how we do it. Now look at this. Can you read it? I think you can. But it's a complete mess, right? But I've done this in class, and people have no trouble. According to research at Cambridge University, it doesn't matter what order the letters in a word are. The only important thing is that the first and last letter be at the right place. The rest can be a total mess, and you can still read it without problem. Now look at that last point, that last sentence, because I just want to make a point about how not really how we perceive it, but how we're able to interpret it. We're able to see that sentence as this. This is because the human mind does not read every letter by itself, but the word as a whole. This, by the way, is a meme that I'm sure some of you have seen. It's been going around for quite a while, and there are variations on it. And it looks like a case of recoding, right? And that is how we read. Now, I need to add that although this phenomenon is obviously real, what they say here is strictly false. It did not originate with researchers at Cambridge, and it doesn't perfectly generalize to all sentences or words because there are times when you can be confused. You can maybe think it's another word or something. Yeah, it didn't come from Cambridge. It came from someone's dissertation and quite a while ago, and maybe in the 60s or the 50s. Okay, another point about this is that recoding, although it makes it easy for us to read normal English and messed up English, like we have up here, it does have a downside. It makes it harder to find typos. And nowadays, our computers correct things for us. But imagine you have printed something without making corrections, and the corrections weren't automatic, and now it's printed and you're running across campus looking for typos on this printed paper. How do you overcome the recoding, the effects of recoding? Well, in the old days, newspaper editors would address that by reading backward. So that forces you to look at each word out of its context and to actually look at the letters and the order they're in. So scanning back, I don't know if that counts as reading, but scanning backwards is a good way of detecting errors. Also, handing it to someone else who is not familiar with what is written helps. Okay, that I think should just about do it. Next time we're going to look at these questions, so you might want to look over these questions now that you've gone through all of this and make sure you can answer them. I will send you instructions on what to do with 20q.net, and we'll probably do a little bit of review. Of course, I always leave time for your own questions as well next time. And then we'll move on to, what's the next slide? Yeah, we're going to talk about totes. Okay, good.